Dr. Bush.
Okay, very nice talk. I've got a couple comment and a question. The comment is this: you talk about electrons, electron wind coming off of that, and that would be consonant with one of the things that I mentioned in my talk. The other thing is this: you have to have a wind of deuterons usually in this thing to get heat. Now, how does that work in your theory? Because it seems to me all you need is the deuterons in the lattice with no exterior wind of deuterons to keep this thing going. So how do you get around that?
Well, this is a kind of a reaction between two stationary states. We're not talking about how the deuterons get replaced by, say, diffusion and the conversion of chemical deuterons to band state deuterons. This is just the basic process of one pair of deuterons turning into a helium atom.
Okay, except if we stop the current, the excess heat goes away so fast, you'd be shocked if you haven't done the experiment.
Except heat after death.
You can get heat after death, but you can account for that
I'm just
from
trying to
an
show
interior
you.
current that's now working its way out.
I'm not telling you how the whole electrolytic cell and the whole process of getting things into band states and all that.
No, but you see my point? I'm saying that it seems like in either heat after death or the regular thing, you've got to have have to have a deuteron wind. And I don't see that enters into your theory at all here.
Well, this doesn't treat the diffusion of deuterons to replace the ones that are converted to helium. No, that's a different part of the problem. This is talking only about conversion of deuterons and how the Coulomb energy, Coulomb repulsion, doesn't really play a role if you get things into this state where you have correlation avoidance.
But I'm still not sure you see my point. I'll talk to you afterwards.
Yeah. 10 to the minus 12 seconds, you're getting diffusion. Nothing moves in 10 to the minus 12. I mean, in a diffusion through the crystal, you wouldn't get any movement. So that, you know, in the 10 to the minus 12 seconds that it takes to go through all the relaxations, you really wouldn't.
But again,
have
he's not
diffusion.
bringing in any, he doesn't have any wind anywhere, of deuterons anywhere in his model here.
Well, I'm not
Yeah,
explaining everything.
This is
Wait a
just that
minute.
little one.
Well, that's the problem in cold fusion, because if you don't explain everything, you've got, you know, loose things that...
That does bring up another unexplained point. It seems in this you would get essentially every other, I mean, some of them would have spins wrong, half of them, so how do you...
Probably
account for the-
1 out
it's
of
about
9
1 out
has
of-
correct spins.
1 out of 9?
And you have to take that into
Because
you can actually use this theory to calculate reaction rates.
Okay, but we had 4,000 watt, 3 to 4,000 watts per cubic centimeter. That's only about 1 fusion out of every 12 trillion pairs of...
Well, we calculated reaction rates versus concentration based upon certain Fermi golden rule and certain fairly simple assumptions. And your reaction rate goes as the square of the concentration of band state ions. And it's not hard to get a kilowatt per cubic centimeter, even with only 1/9 of the pairs being active.
Oh, that, actually, my question is the other end of it. How does your theory account for the fact that there are so few fusions among so many deuterons in the lattice? I mean, a power rate of 3 or 4 kilowatts is really only 1 pair fusing per second out of every trillion or so.
Well, this theory only involves those deuterons who are in band states. In palladium, most of the deuterons are in chemical states.
Oh, okay.
Very much most of them,
Very
like
much by
all
factor
but
of
maybe
trillion.
10 parts per million.
Okay.
But still, the concentration in band states is enough to give you
It's
this
enough to
1
do it.
kilowatt. Now, if you could get fusion in something like nickel or silver, that wouldn't be the case. But after all, with palladium, we seem to have to, at least presently, working with a host that's essentially PDD.
I guess take one more question, then we need to move on to the next.
Okay, again, your ideas are very interesting. One last question here. Would your band theory allow you to predict the rate of fusion?
It does, yes.
Would you
Now, I
present
can't
that
say
at
that
some
it's too
point?
accurate, you know.
Yeah, okay.
It does give a rate of fusion by Fermi's golden rule, which is the reaction rate between stationary
That'd be
states.
nice for you to present that someday.
Okay, it's in our 1991
Oh, is it?
paper, actually.
Okay.
Chief, you have a question, Mike?
Just one comment, and I wanted to go back to the first part of your lecture and make sure that a point isn't missed. The fact is, as we have confirmed, at least in a preliminary way, Arata's double-structured cathodes seem to be able to make excess heat in a consistent way. And this is a very important fact. I don't know that the reason for the reliable reproducibility of that geometry is the idea that Arata had in mind when he originally made it.
I agree with you.
But it's still a very important fact.
And I don't know whether the heat that Arata sees comes from the powder, which is a very small fraction of the total mass of the system, or whether it's from the palladium bottle. But either case, the amount of heat is much more, a higher total energy per molecule than you can get by chemistry.
But didn't you show that his data for the solid cathode? With
Yes,
that
he did not
ACS?
get excess heat with a solid cathode.
But you don't see that as equivalent.
So he needs the power.
I don't consider that equivalent to the bottle necessarily, and I've suggested that he run empty bottles.
The powder is back to surface effect again. I mean, it seems like that would be easy to determine whether it is the powder or the other.
Well,
If it's the powder, it's the surface effect.
I think if he ran empty bottle versus bottle with powder, we might know the answer, but, you know,
But there's
experimenters
not-
have their own way of wanting to do things.
There's not necessarily one mechanism.
Well, that's true. It could be more.
I think that is a great danger to work out a theory and say, you know, that is explains everything. It isn't. I think that the Arata's
Could be
system
several.
is really quite different to the thing which we described. Yeah.
And I'm not saying that our theory is really very different from Preparata's in some way, because we really, when we talk about pairs in this talk, we're really talking about approximating a many-body system with a sum over pairs, and you know, that's a great simplification.
Well, I hope in Washington we can have a major session on the different ways of discussing this.
I think it would
Because
be
that's a
fruitful.
major undertaking to see what the commonality, what is the difference between the theories, really? Is there a difference?
Yes.
Is there no difference? And this has to be stated at some stage.
And how do we observe
Because we
that?
talk in such different languages, it's really, as you say, we've
Is
got to knock
it
it
a
out.
linguistic problem?
It is a linguistic.
sociological.
No, Preparata comes from.
You get that many
field
neurons, it
theory,
is.
you know.
Yes.
Everybody comes from a different perspective.
Right.
But in the end, it may be the same thing.
Well, certainly, I think we're closest in our thinking, but we do look at it from a different
Well,
sometimes.
let's thank Talbot Chubb.